Hey everyone, in today's video, we're going to be solving the problem kth smallest element in a BST. So the question says given the root of a binary search tree and an integer k, return the kth smallest value, one indexed of all the values of all nodes in the tree. Okay, so what the question says is that let's assume, let me just remove this. Okay, let's assume you have a binary something like this, right? And it says find the kth smallest element, which means that let's say if our k is equal to 3, right, we need to find the third smallest element in our binary search tree. Now, if you think about it, what is going to be the third smallest element in our binary search tree? Let me just remove this tree over here. It's not a binary search tree. I made a wrong tree. Let me just write this properly again. So let's see. We have a tree something. Wait. Let me just make it again. Okay. So let's see. We have a 6. Let's say we have a 5. We have something like 10. We have 20. Then we have 13. Sorry, this is not 13. This is going to be something like 12. Oh, this is not 12 again. So 8. Um, this is our tree, and let's say we have something like let me just remove this portion and write it again. Let's say we have something like 4, 5, 6 here, and we have something like 1 or 2. We have 1 here and we have 3 over here. Okay, so let's say we have a binary search tree something like this. Cool. And let's say we have a k equal to 3. If we have a k equal to 3, which means that we need to find the third smallest element in the binary search tree. Right. Now, if you look at this binary search tree over here, what can you say? What is the third smallest element in this binary search tree? Right. If you see over here, you see that 3 is the third smallest element. Right. 3 is the third smallest element in this binary search tree. Right. Now, how can you basically solve this problem? Now, if you think about it logically, do you know what the property of in-order traversal is in a binary search tree? So if you have a binary search tree, let's say if you have a binary search tree and you apply in-order traversal on it, in order traversal on it, do you know what you'll get? If you apply an in-order traversal on a binary search tree, you get a list of nodes. Let's say if you're going to print out all the nodes in an in-order traversal, you'll get all the nodes in a sorted fashion, right? If you print out all the nodes of a binary search tree, the nodes are going to be in an in a sorted fashion, right? So let's just see this out. Let's check this out, right? Let me remove all of this. Okay, and let's do this. If you're going to print it out, right, in order fashion, what's going to happen? Follow the pattern of left node and right. If you follow left node and right, what we'll do is we'll go to the leftmost node, which is going to be 1. We go here, here, here. We go to 1. We'll print 1 out. Then we'll go to 2. Go back to its node. We print 2. Then we go to right of it. We go to 3. Then we go back to 2, and then we go to 4, which is two's node. We print that. Then we go to right of it. We go to 5. Then we go to five's right, which is going to be none. If you have none, we go back to 5. Then we print out 5, which is going to be the node. Then we go to 6, which is the right of 5. Then we go to the left of it. We have none. Then we go back to 6. We print 6, right, which is going to be the node. Then we go to the right of it. It's going to be a none. Then we go back to 6. Then we go back to 5. Then we go back to 4. Then we go to 7. Now, when we go to 7, it's going to be the node, and we're going to print 7 out. Then we go to the right of it. We go to 10. We go to the left of 10, which is 8. We go to the left of 8, which is none. We go back to 8, which is going to be the node. We print node 8 out. We go to the right of 8. You have nothing. We go back. Then we go back to 10. We print 10 out. Then we go to right, which is going to be 20. The left, you have none. We go back to 20. We print 20. And then we go to right. We have none. Right? So this is what the in-order traversal is. Right? If you look at it, what have we got? We got a list in a sorted fashion: 1, 2, 3, 4, 5, 6, 7, 8, 10, 20. Right? We got the whole list in a sorted fashion. Cool. So now you understood what in-order traversal is, right? So basically, if I tell you how to solve this problem, basically you can just solve it, in order fashion, right? If you solve it in order fashion, you have 10 and 20 over here, right? What you can just do is, like, the extreme brute force approach is following an in order traversal over here, And if after following an in-order traversal, you can just loop through the list and find the third smallest element, which is 3, and return that. Right. This is the extreme brute force approach. Cool. Now let me just, remove all of this clutter which I have. 1 second. Okay. And almost done. Yeah. So 1, 2, 3, 4, 5, 6, 7, 8, 10, and 20. Right. This is our in order fashion. Right. The extreme brute force approach would be to follow the in order traversal. And if you follow the in order traversal, what would be the time complexity of the code? It would be an O of n. Right. The time complexity of the code would be O of n. And for looping through this list and finding the third smallest element again would be O of n. Now in an in order traversal, the space complexity would also be an O of n. Okay. Now, so if you follow this method to find the binary, to find, you know, the third smallest element using in-order traversal, iteratively or recursively, right? Either way, if you follow it using a recursion or iteration, it will give you a time complexity of O of n and a space complexity of O of n, because an in-order traversal has a time complexity of O of n and space complexity of O of n, right? Now, but this is actually the very brute force approach, and you can find the recursive approach on my channel. I'll be linking it up right over here. I'll be linking it up. You can just see in the suggested videos that might be, popping up right now. I'll be okay. So you can see this recursive approach which I've done. Okay, but that's not the way to do this problem. So how can you do this problem? Right. If you check out my way to do this problem is using Morris in order traversal. Right. And why do we need Morris in order traversal? Is because it's going to give us a space complexity of O of 1. Right. Morris in order traversal is going to give us a space complexity of O of 1, which is much better than O of n that you get from normal recursion or iteration. Right. So the problem is pretty straightforward, and we're going to solve it using Morris in order traversal, and we're going to get our output. Right. And if you haven't checked out my video on Morris order in order traversal, you can do check it out. I'll link it up over here as well. Check it out. You'll understand how to use the Morris in order traversal approach, and you just have to make like 2 lines of, or maximum add 4 lines of code in that, or just to make very small changes to that code, and you'll get the output over here. You'll get the output to how to solve this problem. And just to refresh your memory, what is modern in our traversal? It just is threaded binary trees. What you basically just do is, just to give you a very small recap on it, you'll just take our current node, which is going to be this. We'll go to our current node's immediate left node, immediate, D-I-E-T-E, immediate left node, and we'll go to its rightmost node, and we'll make a thread over there. So what I mean by that is, let's say if 7 is our current node, we'll go to its immediate right left node, which is prev, and we'll go to its rightmost node, which is 4, and we'll make a thread from 6 to 7. Then we'll go to 4 as our current node. We'll go to its immediate left node, which is 2. We'll go to its rightmost node, which is 3, and we'll add a thread from 3 to 4. Then we'll go to cur equal to 2. Then we'll make our prev equal to 1, right? So since prev doesn't have any left node or right node, this is going to be the rightmost node itself, and we'll add a thread from 1 to 2, right? And similarly, from 7, if we have 10 our current node, we'll go to our left node 8, immediate left node, and its rightmost node is itself, which is 8. We'll add a thread from 8 to 10 like this, right? And that's it. Basically, these are all the additions you have to do to make it a thread binary tree. And do check out my video, because it's a pretty long video which I've done on 30 minutes long. So explaining the whole concept again would not make any sense. Just check out that video and come back over here to see how we're going to solve the problem. And I'm just going to show you the code, because if you checked out that video, you already know what the code is, and you just need to make like very minute 2 lines or 3 lines of code changes to that code to get the output over here. So let me just show you the code for the problem. So this is what the code is like. And if you check down my video, you know that the whole code is the same. The only difference over here is that we haven't made like an in order list, which we made over there, because over there we printed it out in an in order fashion. Here we're not going to print that. What we're going to do is, while we loop through the list, right? While we loop through the list, okay, So let me just explain it to you in a better fashion. Let me just rub everything over here, declutter it a bit. So if I remove everything over here, okay, give me 1 second, guys. Okay, and let me just remove all these curve words and all these things as well. This, cool. And let me just make it again. This is 7, 10, 4, 2. Okay, so this is what is our thread binary structure, right? So what we're going to do is just basically simple. We're just going to loop through the list like this. We're going to go to 7 from 4, then we're going to go to 2, we're going to go to 1. Then when we come to 1, we see that it's pointing to 2. We go back to 2 over here, right? When we go back to 2, then we go to 3, it's right. And what the only difference over here is what we're going to do is while we do an in-order traversal, okay, while we do an in-order traversal, we'll just keep on decrementing the count, right? So in our previous code, where we were adding the elements to our list, right? If you remember, this was the line just above this curve dot right. We were adding the elements to the list, and just above this line curve dot right, again we were adding the elements to the list, right? So what we just need to do is, besides just adding the elements to the list, right? What we're going to do is we're just going to decrement the number of k elements over there. So what we do is we just reduce k by 1 minus equal to 1. And what that would do is if 1 is getting added to the list, it's going to decrement the counter of k by 1. So let's say if k is 3, it'll become 2. But that means that 1 is getting added to the list. Then we'll go to 2. Again, if we decremented k minus equal to 1, that means that 2 is getting added to the list. So this becomes 1. And when we add 3 to the list, this means that k will again equal to 1 minus 1, which is equal to 0. This means that we're adding the elements to the list. And at any point when k is equal to 0, right, we'll just return that current node value, which is basically 3 in our case, and we'll get the output, right? So we don't even have to traverse the whole list. At any point when we hit k equal, becomes 0, we'll just return the output of the code, right? So this is what the code is, guys, right? If you see over here, we were this line, these three lines of code are the only things added, and these three lines of code are the only things added, right? If you remove, if I remove this thing and write in order dot append per.val, it basically just means that we're appending the current element of the node in the list, and over here is the same thing, we'll be appending the current element of the node of the list, right? And besides that, we're just decrementing the counter of k, and we're just checking if k is equal to 0. At any point if k becomes 0, we just return the current val, which means that that is the smallest element in a BST, right? That's it, guys. That's all you have to do. That's just 6 lines of changes in the code, and that's basically just, right, in the same 3 lines of code that are getting repeated twice, right? So it's basically 3 lines of code that you would change in the models in our traversal code, and you get the whole output of this answer. And it has a much better space complexity than recursive approach, which you can also check out on my channel as well, right? So let's run the code, guys. Yeah, it's running, and let's submit the code. Yeah, the score is submitted. So yeah, guys, that's all for today's video. If you like the video, do like, share, and subscribe. Do let me in the comments what I can do better to teach you guys these concepts. Also, let me know if you have any specific videos or questions in your mind that you want me to do. I'll do solve those problems as well. Besides that, do check out my podcast. And until next time, guys, thanks for watching.